Oh, the lower one?
Wasn't high enough, I had to tape up the...
Yeah, that's why this is dark, because he taped that thing up there. So that's the best we can do. As the sun moves up, that'll disappear, but that's just the way we are now. Okay. Yeah, we got to wait till the sun goes away before we can study the subject, right? Well, I find this an exciting time. For one thing, these telescopes give us a real window into the universe, and it's told us everything we know about what's really out there. With this archaeological discussion of how we found out about the sky and so on that we're having the DVD series over at Climb, we're finding that, they looked at the stars in the sky, and they looked when the sun came up at different locations throughout the year and so on. So they kind of got a handle on a lot of the things about the star movement, even the precession of the Earth's axis, and a whole bunch of good things like that. But they didn't have any way to see beyond those little white spots called stars. And we know that a lot of them are much more complicated from that. But we only know about that because of telescopes. And I'll tell you about how we're really moving forward dramatically to talk about those things. But I'll talk about each of these in turn as we get there. These are the kinds of things that we can see now, and we can see in detail within those now, which they had no idea about before. That might be just a little more fuzzy than some of the other stars up there, but that's all they knew. They couldn't tell any more detail about it. This is part of the life of a star. This, again, is something that they had no idea about. Sometimes they did. There was a case where there was a huge explosion, so they saw this little bright spot get brighter and brighter, and then it kind of dimmed, but they didn't really know why or anything, It's the way it goes. Part of the history is, first of all, to me, how long it took to make telescopes. They knew about eyeglasses and used those for reading back in 1286. Actually, even before that, the monks were using some pieces of glass that were curved, but they weren't really very good lenses. Then they started shaping lenses for eyeglasses in 1286. But a telescope that Galileo had is just two of those lenses. So you have a lens here, and you put it here, and you look through them, and you got a telescope. The idea to think about doing that was really difficult. Now, it's so obvious, and Galileo really opened up the universe by looking out and seeing the moons going around Jupiter, as well as the mountains on the moon. Then Newton not only discovered gravity, but he also invented the first reflector telescope. And I'll show you pictures of these in a little bit. And he did that himself. And not only did he invent the idea of using a concave mirror and a little lens to make a telescope of that sort, he actually ground his own mirror because he couldn't trust anybody else to do it. He was so far ahead of his time, that just couldn't happen. Okay, and then Christian Huygens compounded eyepieces, so that's a more complicated, more specific kind of thing than achromatic lenses, that is color-corrected lenses, which is we take for granted all the time. And I'll talk more about all of these issues in a little bit. And then Herschel's large reflector telescope. We're talking 4-foot diameter reflector mirror, okay? That's huge for the day, and that's nothing for today, for our day. I will mention that these telescopes, I have back here a pair of telescopes, and it shrunk to this way. It's called binoculars that everybody uses, because we also put prisms in there to reflect it back and forth so it doesn't have to be a long telescope like you see the guys out on the ships, bouncing around trying to keep your eye on that. Well, we can shorten them. And then in addition, I have another telescope which is similar to Newton's reflector telescope, a little thing out here, and you can look down inside the front and see the mirror, and it comes out, and I'll show you how that works here in a little bit. Those things are so good. One of the problems with this one is the image is upside down because I don't have an erector prism in it, but it's looking good for looking at birds and some flowers and stuff at over distance, and it's just kind of fun to play with, especially for kids to play with. I got that off the internet for $20. It's incredible what you get. I think new, you pay $50 for it. It's incredible what you get these days. So anyhow, let's move along. Here's Galileo's telescope. The top is 14 power. and the bottom one is 21 power, 2.5 feet long. So that's what he used back in his day to study and see the first planetary motion around the planets.
Got him in a lot of trouble.
And it got him in a lot of trouble because he started making things about mountains on the moon, and the moon was supposed to be perfect sphere. And he said, no, surface is rough. There are mountains. I can see shadows. And so another ding, anti against him. Here is Newton's reflecting telescope, 35 power. It's really only about so long. It's shorter than the one that's back here. Small but effective. And people could hardly believe it. He took it to the Scientific Society in Britain at the time, and they just couldn't let it alone. They had to pass it around. They were really impressed with it, and they should have been. They should have been. It's only 6 inches long, okay? Really amazing. Carry it in your back pocket almost. This, on the other hand, is the 40-foot telescope. The mirror is this. This is Herschel's metal mirror. He would polish it up, okay? And they didn't have good things like aluminum and other non-corroding things like we have today. So every month or two, he'd have to polish it up again. But you had to be careful you didn't screw up the angle of the surface, because it had to still focus things well. And of course, moving it up and down wasn't so easy either. You had to have a fancy ropes and a lot of effort and so on. And of course, you got to track something around to really make big observations on it. So the wheels here, and you had somebody. Now, all these guys that were scientists, Newton and all these guys, had a lot of money. They were independently wealthy, big estates and so on, which is why they had the free time, for one thing, to do it. And also, they, like guys like Herschel, he had the money to be able to build stuff like this and then pay people to help him move it around and do things. His sister was really instrumental in doing a lot of things. She discovered several comets, made a lot of independent discoveries herself, even though she was just a woman. And in those days, that was significant. She was just a girl. Girl power. Let's talk about the telescope basics, because that's really what lays the groundwork for where we're going with the modern day telescopes. Whenever you have light refraction and dispersion in any kind of lens, any kind of glass, you've seen it in a prism, and you see this beautiful spectrum laid out over here. Well, if you have a simple lens, the same thing happens. As it comes in here, the light changes and goes in different directions depending on the color of the light. So if you just have a simple lens, you don't notice, you'll notice color, but you won't notice it laid out like this. This is exaggerated a little bit. They come to focus at different points. So you've probably seen cheap optics where you see a color ring around something. So you try to correct it and have achromatic lenses, that is, color-corrected lenses with multiple surfaces, and also the different glasses have different characteristics about dispersion of the light. So they arrange these so that they offset each other a little bit, so you end up with a better focus, but it's still not 1,000%. It's still not perfect. On the other hand, if you take a mirror, you know, every color bounces off a mirror the same way. That's why whenever you look in the mirror to comb your hair and all that kind of stuff, you're not fuzzed with color. You're just right there, and no color images around the edges. So that's what we're really looking for, to get something that's that effective and that good. Only one precision surface do you need. You don't need a front and a back or intermediate things to color correct. You just need one surface. So if you can make that and make it really accurate, you're in great shape. So here's the problem you have. This is actually the type of thing that Galileo had initially. He had a convex lens and then a double concave lens back here for his first telescope. These are some of the telescopes. This actually is a 21-inch Sproul telescope at Swarthmore College. I made a bunch of bucks by taking pictures with this. Very cumbersome. It had a weight-driven drive to keep it moving around, but it's not good enough to make good, sharp images. So I had to sit there, and there are big ladders that go all the way up to here, okay, curved like this as the telescope would swing. So you'd set it up in a general area, and then you'd sit there for however long the exposure had to be taken, and you would have little worm drives that you would hand move to keep the guide star in the right location on the crosshairs, so that the whole plate, you were taking plates that were like about 6 by 10 or something, okay, photographic plates. So you'd get a thing that you were to make a measurement on, you pull out the plate, you set the thing up roughly, you find your guide star, and then you sit there for 2 minutes, 20 minutes, in a cold sometimes, which is why they paid you, and take pictures. The biggest one that was, and also of course the lens is up here, and here's where you take the photograph back in here. So you have to take the weight of that lens, which in this case was about this big in diameter and this thick. So I don't know what it weighed, maybe 40 pounds or so. So you need, in order to keep that very stiff, you had to have a pretty strong metal tube, a lot of weight. Same thing over here, it showed big time. 41-inch Yerkes was the largest refractor ever made. Now you have to make those edges of the glass very accurately, this is the whole staff that's used to take the pictures, analyze the pictures, and all that kind of good stuff. Okay, here's the Newtonian, where the starlight comes in, bounces off this mirror, comes up, and because you don't want to put your head in here to see the image formed here, because that blocks the starlight, right? That doesn't work too well. So you have a little mirror in here that pops it off to the side. That's the kind of telescope we have back here. Okay, a better way perhaps is to put a little mirror up here and bounce the light back through a small hole in the mirror, and you can stay down here and you don't have to be up here. For one thing, if this is a big mirror and this is a long telescope, so on, to sit you up here is an awful lot of weight they got to put up there also. Some of the big telescopes, the Palomar telescope, just that. They have a big box for the person to sit in out at the focal point, so you can guide, so on. All that's done electronically now, and they, as you'll see, they make telescopes really quite differently. Instead of having something like this where you're back here, now they put instruments up here, for instance. That's one way to do it. There are all kinds of things that we can do with electronics and photosensitive things that we couldn't do before. And I don't have time to go into all of them, but there's a lot of them. Now, one of the other difficulties is the Earth rotates. So if I am sitting here or standing here or whatever here, and I want to look at that star, and I am my telescope there, well, the Earth is rotating. So I have to keep adjusting my telescope all the time, okay? So that means that you have you have an Earth that's twisting around the pole like this, and so I have to have, for one thing, I have to have a little platform that puts the telescope at the correct angle so that it's parallel to this line, the axis of the Earth rotating. And then I also need a clock drive that moves it once in 24 hours in order to keep following the stars. So I can put a plate in the back of this, and the telescope moves in such a way that the stars are staying in the same position with respect to the telescope, and I can take my long time exposure, whether it's electronic or photographic as in the past. And of course, different places in latitude have different angles that you have. So all the telescopes these days are made with these kind, even the amateur telescopes, which is one here. You can see here's the axis that you line up with the Earth's axis, and then there's a clock drive in here that will slowly rotate this around. And here's just some examples of things. Here's a big example. This is the one that rotates, okay, combination of complicated things. One of the other difficulties is we're interested in looking at stars, but stars have a lot of emissions. They have infrared because it's hot. They have light like you and I see. Some of them have additional things like X-rays. We'll talk a little bit later about there's an awful lot of microwave energy that comes from them, and we'd like to study all that stuff. Well, the atmosphere doesn't pass all that stuff. So here's an indication. Here is radio telescopes are in this. Here is our visual red, white, orange, yellow, blue, green. And then there are X-rays over here. Here's ultraviolet. Here are X-rays, and here are gamma rays. And a lot of those don't get very far through the atmosphere. Okay, this is absorption. So maybe this is sort of where we are and where the highest telescopes are at about this level. So all this stuff is absorbed above that because there's still most of the atmosphere is up there. This is maybe a better way to look at it. Over here you have radio waves observable from Earth. Here you have the spectrum. Some of it gets through, different amounts. Red doesn't get through as much. it's absorbed. Gamma rays, ultraviolet, so on, pretty much blocked. So you can see that it's a real problem depending on what it is that you want to save. So let me show you what is seen by some of the different things. If we take a look just at our galaxy, okay, so the plane of the galaxy is right here, and we take a picture in that direction. Here's what it looks like with just detecting gamma rays, this kind of energy, 5 times 10 to the 7. Here's X-rays, here's ultraviolet, here's visible. That's what you see whenever you go out in the night sky in a really dark sky and you see it. And then we can see also infrared. And here's microwave, and that's been significant about determining the origin, the Big Bang origin of the universe and so on. And then radio, 21 centimeter. 21 centimeters, a particularly interesting wavelength, and I'll get to that in a little bit. And then this is radio, 73 centimeters. Doesn't mean that much. We can't spend time going into all this stuff. Infrared astronomy. Here's Jupiter in the visible. Here's Jupiter in the infrared. So different wavelengths give us different information about these different things. Here's Orion. Here's the belt of Orion. Here's the sword and so on. And here's what it looks like in the infrared. And we know that in Orion, there are an awful lot of stars being formed and all those gas clouds that are there that we can see in this infrared picture, but not in this one. And we have here a satellite that goes above the atmosphere to take a look at some of those things. Here's the bunch of telescopes in Hawaii. Altitude is about 9,000 feet. Almost 2/3 of the atmosphere is below that, so they're getting up there. That's really kind of neat to be able to do that. And here's what all these are. Several different things from around the world. People come over here and put their telescope in, and these telescopes are not cheap. We're talking multi-millions of dollars, hundreds of millions of dollars of money, for instance. One of the other difficulties, okay, we'll take a look at this particular one a little bit closer. And the mirror in that is 8.2 meters. That's about 25 feet in diameter. That's from about here over to there. And we have a couple of them. One of the problems that they're starting to run into now, because they keep wanting to put up other telescopes in Hawaii at other mountaintops and so on, same kind of thing you find out here with the Native Americans. Hey, that's our holy ground. We don't want you messing up with that mountain. We want to go up there and pray and have our things and do things. So there is some resistance to that because the mountaintop is sacred. And you have to respect some of those things. Here in Chile is another one. The altitude of this one is 7,200 feet, above about 25% of the atmosphere. One of the advantages of this is it's able to look at the southern hemisphere, not just the northern hemisphere. There's stars down there too. We don't ever see them, but they're there. And I've never seen the southern sky. I've never been south of the equator, so I'm really disappointed. I haven't seen the Southern Cross, and apparently the Milky Way is even more spectacular down there than it is up here. One of the other points I'd like to make is that a bigger mirror is better, because whenever you have a small thing, the light has an interference thing about the smallness of it. You've probably seen these light coming through the pinholes, maybe of an umbrella or a tree, and you see this rainbow color spread out. That's because of the dispersion. And it turns out that if you have a couple of those things, you can't resolve it because the light spreads out from small holes. That's true with bigger holes also, so you can only focus it to a fine enough point where those effects of the width of the thing that you're observing it with start to interfere because of the wave nature of light. So the idea is bigger is better. Here's a small aperture with two pinpoints of light like this, and if I make a bigger aperture, I am able to resolve them a little bit better, and if I get to an even larger aperture, I can actually resolve them into two stars, okay, instead of having everything all fuzzed together. So that's another reason to drive to larger things. Not just the fact you're collecting more light, but also the fact that you can refine the images much better using those. Okay, glass removal is needed to go from a circle to a parabola. So if I have a big flat piece of glass, and we're talking something, 25 feet in diameter, maybe, I got to shape that. And if I make this blank, I'm probably making it in an oven where it's just a flat hunk of glass, okay? Well, I got to scoop out a lot of that to shape this form that I want in order to be able to focus that? Well, I can easily make a sphere. That's a little fairly simple. I can even maybe try to cast it that way. I really need to have a parabola. And one of the things that I can do is I have to get rid of all that glass in order to be able to end up with a mirror that's like what I want. Actual mirrors are often more complex shape with even more curvature and multiple surfaces that give a much faster F ratio of 1.2 to 1.4. Photographers probably know what I'm talking about with that. I don't have time to go into it too much here. Okay, another way, well, there are two things. One is rotating oven decreases the glass that must be removed by grinding. You may not realize it. You probably all at some point or other have swirled a bucket, or you see water swirling around, and it goes down in the middle because centrifugal forces push water out to the side. And since water is flexible, it goes out to the side and it gets deeper at the edges and lower in the middle. Well, it turns out that if you're very careful about how you rotate that, that's a perfect parabola shape. So if I could take molten glass and swirl it around like that all the time, it would form into the shape that's pretty much what I want it to be. And I let it cool down. Now, we're talking big chunks of glass, so you're talking about letting it cool down over a period of 6 months. And you're talking about something that's 15 feet in diameter maybe, and you're swirling that around to get the shape you want. Okay, well, I'll show you that's exactly what they do. In addition to that, if I'm really clever, what I could do is make a segmented mirror. That is, I could make a whole bunch of mirrors this size, which is relatively easy to do, and put a whole bunch of them around. And then if I can very accurately make this mirror in conjunction with this mirror, in conjunction with this mirror, all form a bigger telescope to give me the same really neat image up here, I've collected a lot of light and put it right where I want it. And that's a lot easier to make a whole bunch of them. But now I have to align this one very carefully with that one, very carefully with this one. And then whenever I'm swinging this thing around to move it in different parts of the skies, they get pulled by gravity different ways. So I got to compensate for that. And I got to get these things very close to one another accurately within nanometers. Very tough job, but that's what they do. So basically what they do is make a whole bunch of segments like this. And then each one you have to have properly shaped. And this is only a certain part of a parabola. It's not the same shape as this part of the parabola over here. The same. So everyone has to be independently done and then put together in one nice combination of things. Here's a timeline. 1948, the 200-inch Hale telescope at Mount Palomar. I remember growing up as a kid, that was the mark. That was the biggest telescope in the world at the time. Really a major thing. I see some heads nodding, so people that were paying attention to that stuff know what I'm talking about. Okay, Jerry Nelson is a guy that was an innovator. He had the segmented mirrors and edge alignment and grinding and polishing. And I'll talk a little bit more about that. There's another fellow, Roger Engel, and he's a guy who had in 1987 rotating ovens. These guys are at University of Arizona in down near Tucson. That's really a hub of telescope design manufacturing in the world even. Spin casting large mirrors, stressed polishing lap, honeycomb structure, and adaptive optics. And we'll talk about all of these because that's what's really needed in order to give us the kind of telescopes that we have today. Adaptive optics. I'll talk more about that also. That is, you know, you look at a star in the sky and you see it twinkle. Well, why is it twinkling? It's because the atmosphere is a little more dense here and a little less dense here, so it moves the light coming through it in a different direction. So it's coming over here and it's a little more dense here, so it kind of bends it over here. And now it gets thin again, so the light goes back the other way. So that's what causes the twinkle. Well, you can't get good sharp images if everything is twinkling. You want it to be dead steady. Well, you have to compensate for those changes in the atmosphere up there. You have to know that when the light is going to come over here, I have to make a correction for that and move it back over here. Well, how do you do that? Well, I'll show you in just a minute. The CIA had that down in the early 90s because they had these satellites up that were looking down on the Russians. Well, if you wanted a good sharp a good sharp image and be able to read their license plates and find out who that person is, you had to have a pretty good sharp image. It couldn't be a fuzzy blob. So they were ahead, but of course they wouldn't share that. because you don't want to let the astronomers know, because astronomers talk to each other and the Russians would pick it up pretty soon. So anyhow, they developed a lot of the adaptive optics, and it's worked fine. Okay, so here's Roger Engel, spin casting large mirrors with a honeycomb structure and also adaptive optics. He was very involved in all that kind of stuff, and he's an emeritus professor now, but he's still, I'm sure, very actively involved in some of these things. Here you can see the size of this thing. You can see that it's spinning. You can see the size of it compared to this person here. So I don't know, what is this, 15, 16 feet across? Here it is, it's been opened up. You can see the honeycomb structure behind it to help make it lighter weight, but still very supportive for this really precision surface that you want to have. Loading a rotating mirror furnace, you have these big chunks of really pure glass that after it cools down, it doesn't have a lot of expansion contraction characteristics. They worry about that. We have Pyrex glass, which has less problem with fracturing because of heat differences. Well, this is even better than that. A lot of these things at least used to be made in Germany, and then they would ship the glass over in chunks like this, really pure stuff. Then you put the right amount of glass in here. You can see the honeycomb structure that this is eventually going to melt down into, and then you start spinning it. And then after you get that done, here's the Gemini North 8.1 meter, 25 feet across roughly, 20 centimeters thick. That's about 1.5 feet, right? No, 2/3 of a foot. It's about 8 inches thick. Okay, accuracy of 1/15 of a nanometer. Yellow wavelength is 600 nanometers, and with this kind of accuracy, so this polishing is what's grinding it down to the appropriate shape. So you can spin cast and you get a large part of it, but then you really have to polish that off and make it really, really accurate. Here's some of the segmented mirrors that have been put together. The Keck telescopes, and I'll show you pictures of some of these, and you can see they just build them up. You can make almost as large a thing as you want. Relatively small mirrors that you can make very accurately, but then you have to put them in a structure that's going to be able to move them around and keep them aligned very accurately with all the other mirrors. That's part of the challenge. And oh, by the way, once I get a bigger telescope, I'm looking through a larger swath of atmosphere, which means I'm picking up more variations in density of the atmosphere. If my variations in density are, like this, well, okay, if I have a small mirror, maybe I have this and I can correct for that. But what if I have a big mirror and here it's this way, over here it's this way, and over here it's this way, all different compensations needed because I got to worry about getting them all back to a nice fine point. Well, then we have to worry about that, and that's exactly what they do also. Okay, here's a guy, I'm getting off to segmented mirrors now. He unfortunately died. He passed away in June, I think. He was 73 years old, something like that. And he devised segmented mirrors, edge alignment as if it's one piece, within nanometers. Grinding and polishing, each blank had 24 tension-producing attachments on the edges as it is ground to a spherical shape. When the attachments are removed, the blank relaxes into the appropriate parabolic shape. So you get a chunk of glass, and then you put torsion on it in such a way that it bends it so that if I make this a nice smooth spherical surface, which is a lot easier to grind than some complicated surface, and then I take those clamps off the back and it warps back into the space you really want. If you can do all those calculations because you know the characteristics of the glass and you can grind a uniform spherical kind of thing much more easily, but you have to do the calculations, and that's pretty simple, and you have to put things on and torque it just the right way. They do that. So here's the way they would torque these things. This is a pivot, but all these things are strong attachments to the glass, and then when they let it relax, it comes back into a nice shape that they want to have as appropriate, depending on whether you're here or here or here or here. And you have one big nice parabolic thing for this mirror. And of course here you do it a lot more times, a lot more complicated. Here's the one I showed you before, just showing you more. I should have put this a little earlier. This is adaptive optics I wanted to indicate to you. When I drove down to watch the eclipse, I went down the week before, and it was much hotter, and the air, you know how you've looked at something and it's kind of fuzzy when it's hot because the atmosphere is churning and moving and so on. So what I saw was this from a distance. This is a picture I took of that thing that I showed you here. Okay, I was down here pretty far. This is fairly close. Then I was down here maybe 100 yards, and I had my telephoto, and I took this picture, and then as I use my adaptive optics, I go to something like this. So that's kind of showing you visually what adaptive optics will do. And really good adaptive optics will do even better than this. Okay, here's how adaptive optics works. It turns out that there's a natural layer of sodium atoms all the way around the world, way up high, about 50 miles up, I think it is. Do I say here? I don't. Maybe it comes up a little bit later. The idea is that I take a laser here. Here's my telescope that I want to take pictures of. I take my laser here, and the laser is such that it excites the sodium atoms to emit light. So I know that this is right in the direction of all the atmosphere that's going to affect the shape of these star lights points coming in. So I know what this is because I put it there. I know its size, shape, and all that kind of good stuff. And then I can analyze the image that comes back to the telescope, that the image of the telescope makes, and then I can adjust the mirrors. Well, I have a separate mirror that's flexible, that I can move back and forth and around to compensate for what the atmosphere did. The atmosphere goes one way, I have my mirror go the other way. So I can compensate, and what happens is the light comes from the telescope into here, goes down through here. I take a little bit of that light, run it through an image analyzer, run it through a computer, go up here, and then I have a flexible mirror that has all kinds of little things in the back that can change the shape of that mirror just a tweak to get rid of the variations. The mirror, the atmosphere tweaks it one way, my mirror tweaks it the other way, comes out perfect. So I do that across the image of the mirror, and this is what I get. Here's the adaptive this shows how the light is smeared out across the image, and if I use the adaptive optics, it holds it down into just one. So instead of having a mush like this in my receiver, I get a nice, now there's a little mush around here. It's all a matter of how well you can do this. Typical telescope Stirl ratios, forget about the name. The thing is, it's only good as 1%. Old adaptive optics does 30 to 40% correction, and the new adaptive optics 60 to 84%. And this slide is kind of old, so they're up closer to 95 to 100%, or 95 to 99%, getting better all the time. So that's why they can have really huge telescopes, which is really hard to move them up very high above all the atmosphere. You just can't do it. But they can still get magnificent pictures even though they're down in the atmosphere. Now, they're very careful about where they put these telescopes. And like at Hawaii and some of the other places down in South America and so on, they'll go out and they'll monitor the atmosphere for 2 or 3 years to find out which is the most steady atmosphere that they have. Do I want to put my telescope here or there or there? Now, 2 or 3 years may seem like a long time and a big investment, but when you're talking about putting in a couple $100 million and it's going to be there for the next active for the next 30, 40 years, it's worth the investment to make sure you're going to get good stuff instead of junk. So they do that. Here's the back of one of those flexible mirrors that I talked about for a big telescope. I mean, it's getting complicated. But then again, so is your cell phone, okay? We've really made a lot of changes and a lot of advances. Here's the difference. 3.5 meter peak telescope with adaptive optics gives you this. Now this is probably 10 or 12, 15 years old. So I'm sure it's better than that now. Here's the Keck Observatory in Hawaii. It's a pair of them actually. The light is kind of hard to tell, but you can almost see the hexagonal shapes of the mirrors in here just vaguely. So it is made that 0.5 ton is the mirror. That's 1,000 pounds. You got to move around very precisely, and all these things you got to keep the edges with respect to one another very carefully within microns and better. Position twice a second within 4 nanometers. That's pretty tiny. Here's some of the relative ideas, relative sizes of telescopes. Here's Gemini North. Here's the Keck telescope that I just showed you. These are wannabes. So these haven't been made yet, but they're ones they're talking about. Notice they're all segmented because that's the only way. You can't make a huge thing like this. These are feet. This is 30 feet. So this is probably 100 feet across. That's huge. But the light collecting is just amazing. Boy, what we can do with things like that. Here's just another indication of how things go. Adaptive optics, if you get some of these big, huge telescopes, well, you know, you correct for one place above the telescope, that's not going to quite do it because the light is coming down 30 feet away over there, and the stars twinkling over there are not twinkling the same way they are twinkling over here. So I got to correct for a different twinkle there than a twinkle here. So that's why you put in several different anti-twinkle things. Twinkle toes? Different toes, different anyhow. Okay, so here's adaptive optics being used in this. Just another thing showing a publicity picture. Adaptive optics. Now these are all fairly old pictures, so but this is what you get. I'm sure this would be much sharper if I had a more modern picture. Without adaptive optics, this is with adaptive optics. This is Neptune. Okay, here is without adaptive optics from the surface of the Earth. This is with adaptive optics. I'm sorry, yeah. And this is an image from the Galileo spacecraft, so it's over there close, and this has no atmosphere in the way, so you get an incredibly accurate, good picture of what that moon looks like. Okay, some telescopes, optical telescopes, the night sky, solar telescopes, radio telescopes, X-ray telescopes. Every different wavelength gives us information about the stars, and it's different information, but it's useful information because it helps us understand what's going on and understand the universe. The Large Binocular Telescope, elevation of 3,000 meters, that's about 9,000 feet, one of the best astronomical sites in the continental United States. 40-meter high structure shown here houses the Large Binocular Telescope, will be fully operational in 2005, which means it's been operational for more than 10 years now. Okay, this is what it looks like. It's hard to get the scale there, but the idea is that you have a big telescope here and a big telescope here, and it means that you have some effects of having those two separated by a certain amount. That has some advantages in addition to just collecting twice as much light. Okay, the adaptive optic image is 10 times better than the Hubble. Now the Hubble is up in space, and the Hubble doesn't have any atmosphere to worry about, so the image there is determined by the size of the mirror. How, you know, the smaller the mirror, the more fringe you get. Okay, so the bigger the mirror, the better off you are. So the Hubble is a certain size, so it has a certain limitation on the point that it can make a starlight. Well, this is so much bigger that these mirrors are so much bigger, and even though they can't correct them perfectly for the atmosphere, they can correct it better enough so that the image is still better than the Hubble Space Telescope. Now also they have the problems, however, that infrared doesn't come through the atmosphere, so they can't see as much infrared. X-rays don't come, you know, a whole bunch of things. It's affected still by the fact the atmosphere is there, but moving around is not one of them.
Where's this one located?
I'm sorry?
Oh, I see it.
Okay, yeah, here's the scale. So this gives you an idea what the scale is. And it's interferometers, which I don't have time to go into the technical aspects of it, but that's also an advantage. Fully operational January 2008. Adaptive optics, image 10 times better than the Hubble. Here's what each of these mirrors looks like. Okay, honeycomb design. Here it gives a bit of a scale with the people standing around it. So I think it would probably be a little bit bigger than this room, each one of them. Another way that they try to get out of the infrared problem is to put a big telescope up in an airplane and fly it around. And I remember going to a talk over at Reed College many years ago where the guy came that talked about this, and they had not implemented it at that point, and now they've implemented it. And one of their problems at that time was the fact that NASA putting satellites up in space and stuff like that was stealing all the money from these lower level ground-based folks, and that kind of pissed them off. But everybody has their problems, I guess. Future telescopes. Here's one European extremely large telescope under construction in Chile, Artist Conception. Okay, 120 feet across. That's more than a third of a football field. I mean, this is huge, folks. This is just a drawing, but it's under construction. I don't know what the status of this is. I should have looked it up, but I didn't. Here's one of the mirrors for it. Here's a person giving you an idea. Here you can see all the support things for it. Inspectors check out the back of one of 7 8.4 meters. Each of those mirrors is about 25 feet, okay? So you got 8 of those. That's a lot of light collection. The OWL, the overwhelmingly large telescope, 100 meter, that's bigger than a football field. They aren't going to do that, I don't think. Too expensive. Alternatives have been chosen. And I'll show you some of the things that they're going to come up with. We'll take a break in a little bit yet, but there's still a lot to be talking about. Okay, Hubble is one of the main guys, of course. You hear his name because of the Hubble Space Telescope and so on. Really dramatic, really wonderful. Hubble had some ideas about the expansion of the universe. He did a lot of stuff back in the 20s. He's an interesting guy. He trained as a lawyer. He was a Rhodes Scholar. He had some boxing championships in Chicago. Really a multifaceted kind of guy. And he finally zeroed in on astronomy. And so he ended up being in charge of one of the big observatories. And now, of course, he made so many contributions having to do with observing galaxies when they didn't really know much about that. So that's why his name is so very popular. So here is the Hubble Space Telescope as it's being ready to go into space. Here are solar panels to keep things charged up and so on. So they put it up in space, and there it is. I mean, it's just a gorgeous thing here. This is a thing that flops down to protect it if it has to be swung by the bright sunlight, so it doesn't heat up the mirrors and do all kinds of screw up like that. Then they close this, then they open it up again, and now you're able to, the mirror's back here, and you're able to make measurements. They put it up, and this is the first image that came back. It's fuzzy. What happened? A catastrophe stroke, and it's up in space. I can't tweak the knobs and spit and polish it some more. What are we going to do? Well, this is what happened after they made their correction. This is a similar thing. And what they had to do was they sent up a space correcting bunch of people. They had to regrind some things, had a correction of the lens correction lens to slip in, and they also changed out some of the other components at the time because they had increased the technology and they did some other things. But they had to have a space station go up about 2 or 3 years later. And what happened was that whenever they made the original mirror, you're always checking the mirror, the accuracy of the polish and the focus and all that kind of good stuff. And what happened was that whenever they were using this interferometer to check the size of the lens and how accurately these are placed, it turns out they were holding it, and it turned out that it was reflecting off of this holder instead of on the actual mirror itself. That is, instead of reflecting off of this, instead where it should be here, it was reflecting off the holder for that. And that they have perfectly surfaced mirror, but at the wrong focus. It was screwed up. It wasn't even focused because it wasn't a parabolic thing. It was a different kind of thing. Okay, non-reflecting coating chipped off, and that's what caused it. And by the way, well, I'll talk to him. Anyhow, you ended up with a picture like this then after it was corrected. Now, one of the things that was interesting, okay, we'll wait a few minutes. everybody's vying for time with the Hubble Space Telescope. So you really have to lock in and, okay, I got 3 hours on the Hubble. Wow, here's my project. You write up a long thing and then you put it in. Everybody's putting stuff in the hopper, so to be selected is really pretty unique. Well, that went on for a few years, and then this new guy came in charge of it, and he said, you know, what we really ought to do, we've never really done a deep space look at stuff. And the Hubble is above all the atmosphere. We ought to be able to really get a good idea. So let's find a place in the sky where there's nothing and see if we can take a long exposure and look really far back in time and see what we can find there. Well, here's the Big Dipper, as you see, and they chose this is in the northern hemisphere, and then a few years later they did it in the same thing in the southern hemisphere, and they took this little bitty thing here, which is about the scale, and they took a long exposure. And why is my thing not working? Did I run out of batteries? Oh, no, I didn't. And this is the Hubble Deep Field View of the universe. Everything there is a galaxy, not a star, a galaxy. And some of these go back to within a billion years of the blow. We're at about 13.73 billion years of age of the universe. Some of these go back to about a billion. They've since gone back to 800 million years after the Big Bang, okay? So it's really just amazing. Here's the Hubble Ultra Deep Field, like I showed you, and this is the same thing down south. So it's the same in all directions. So there's a huge universe out there that we just are starting to scratch the surface of. Talked about gravitational waves, and that's another exciting new area to go into. SSI class in 2 weeks at this location, the Hubble Space Telescope class, look in your orange book, by this fellow who worked on the construction of the Hubble Space Telescope. So that should be exciting to hear. I got to come over in spite of the traffic and listen to that guy. Should be quite interesting. Now, there are plans to go beyond that and to put up the James Webb Space Telescope, 6.5 meters. It will circle the sun. That is, it's close to the Earth, not real close. It's out beyond where the moon is, but it's going to follow us around the sun in our orbit, so we'll be able to talk to it all the time. But it really is circling the sun, not circling the Earth. The mirrors are of beryllium, coated with gold, so they get a lot of the infrared stuff, because there's a lot of information we can get about the fundamentals of the universe by looking at the infrared aspects of things. It's at a Lagrangian point, so that's so far out beyond the moon and stuff, we send it and forget it, okay, except the transmissions that it's sending back, but forget about any space corrections or anything like that. That's not going to happen. Okay, here gives you a bit of a scale of what it is. Here's the actual telescope, and it's going to be up there, and since it's very sensitive to infrared, it's one of the things we're primarily looking for. You have all these shields back here, which are to keep the infrared from the sun having an effect on the telescope. So you have multiple layers of shields. So it's sort of like having thermopane, okay? It's hot here, and then I put another one, and I have 7 thermopanes, okay, to keep that infrared radiation really in the mud so that I can really look at things. But this gives you an idea what the scale is. This was going to go up several years ago, but they keep pushing out funding and all kinds of things like that. It's not because it's technical, I don't think. But as time goes by and they get more technical expertise, of course they incorporate that in all the new things that they're doing for the Webb telescope. So here's the old one, and here's a person. Here's the new one. Notice it's segmented also. The accuracy of these things is amazing. I think that, I forgot to mention that, I think. The Hubble Space Telescope, when it was up in the sky, if they want to point it to something, they can point it at something and keep it that way accurately for a day. It's like having a dime 10 miles away, and I keep my finger pointed at that dime within the dime 10 miles away. That's how accurately these things are. If you want to get really sharp pictures of stars, like that Deep Hubble thing where they're looking for 2 or 3 days, that's what you have to do, and they've done it magnificently. Radio telescopes. Why don't we let that go and take a break now, and we'll come back and talk about radio telescopes.
what I was wanting to ask, Dwayne, we went through all of this, casting the glass and
Right.
polishing it, but we're manufacturing a mirror. So is it the surface of that glass that's reflective, or does something
No,
else
they
have?
they put stuff on it. Yeah, good point. Yeah,
Okay,
it's not the glass.
okay, so there's
They put on-
a metallizing layer or something.
Right. So I don't know, beryllium. It's a complex compound so that it doesn't oxidize and get cruddy over time.
Okay, and
Yeah.
then the other thing was, if that last scope you were talking about is not circling the Earth,
It's circling the sun, though.
it's circling the
So
sun. Yeah,
it's-
that's
it-
fine. It's like a planet, but
And it's in our orbit.
what keeps it from being sucked back to Earth by gravity? Is it
It's like
quite a
the
ways out, like 2,000 miles
yeah.
out? Or,
There are places where there's sort of zero gravity pull between the combination of the Earth, the Moon, and the Sun, and there are minimal things there, so it won't take much. It can. It's hard to explain, but that's where it talks about the Lagrangian point. There's a Lagrangian point where it's just not going to. Okay, it's like if you have something on the Moon and you have something opposite the Moon on the other side of the Earth, it's going to move in parallel, and it's not going to be pulled.
I can
Okay,
visualize
right.
what you're
Okay,
saying.
okay, great. Yeah.
First of all, I'm very fascinated by what you're presenting here. I have two questions. The binocular telescope, does that give you a three-dimensional image?
No, the stuff is too far out there. They're looking for interference to get a finer resolution of things when they use that. But it's not really three-dimensional. It means that they can get things. It's like effectively having a telescope that's as big as the separation of the two of them. Yeah.
The other is a personal question. What was your profession before you retired? I mean, you have
Oh, I'm a physicist, and I was working with AT&T Bell Labs. But this has been a hobby of mine forever.
Oh, you were not yourself involved in some of
No,
this stuff?
astronomy and stuff. I minored in astronomy as an undergraduate. Like I say, I was taking pictures with the telescope and stuff, and I've always been fascinated with that stuff. And so I was involved with the Radio City Astronomers for a while and so on. I mean, it's always and I give talks on this kind of stuff wherever I can. So I find it just fascinating. And the implications of the Big Bang and all the things we're finding and other planets. I'm going to give a talk about other planets in the wintertime, and what we're finding there is mind-boggling also, and has implications about other civilizations and all that kind of stuff. So,
My son went to college majoring in astronomy,
oh really?
but then he got out of it.
Yeah.
And I want to show you something that I
Let me get my glasses. Oh, solar. Yeah, the total solar eclipse. Very good. Did he take that?
no,
Oh,
I took
okay.
that,
Oh, you did. Very good.
but I took it off the TV.
Ah,
I don't want.
we took ones directly that are like that.
But I sent this to friends and
There you go.
relatives.
Yeah.
They all got it terrific.
Very good. Yeah, that's neat. Good idea. Well, I'm going to go get some coffee. Okay. I put your tape back over there.
Yeah, I found it.
Okay, good.
Make that change.
Window pane, huh? Is the camera still running?
Yeah, it goes for a couple hours, so.
Oh, okay.
I can show you a little bit more about it. I want to take the whole thing back with me because I'm still playing around with it so much.
Right. But we could shut it off during the break, right?
Yeah, but we don't have to because it has more than 2 hours. It has about 2.5 hours of time, so I'm not going to worry about it. If it turns out we have to do that, I'll do that. As a matter of fact, I didn't even turn off it's listening to us right now.
Okay.
It's looking at the room, but it's listening to us right now.
Right. didn't know we had that, you had that much leeway.
Yeah. And I wasn't sure either, and I was happily pleased to find that out.
Okay. You'll have,
Is that your?
no,
I guess it's mine now.
I don't know if that's,
I guess I'll take this one. Great.
That should,
You can sit in for an extra quarter.
I'm trying to get that fan off so you won't freeze to death.
Oh, I see. Okay. That's the problem we had. He climbed up there with that ladder and put that thing up because the sun was coming in. Now, of course, the sun has gone around, so it's
Yeah.
okay. But yeah,
Don't think I'm not interested. This is fantastic.
I know you're not.
3 things to do today.
Yeah,
On my way.
you're doing things with your house and stuff too, aren't you?
I'm trying to.
Or you're done too? Yeah.
Getting
Okay.
bits and things.
Yeah.
Yeah.
Okay.
And it's just, the day goes.
All these things nagging at you. Yeah. Yeah. There's one thing after another.
I really hate having to make decisions about the house for myself.
Are you going to move out and move into a home or something then? Or okay.
No, I just need a new roof. And
Oh, I see. Yeah, that's always a pain. Sure. You betcha.
Where did you get all your knowledge from on this, on the telescopes? Did you have it?
This kind of stuff, I just spend a lot of time at the internet. I subscribe to several science magazines, so I keep that. Yeah, this is interesting. My background is physics.
Okay.
I have a PhD in physics, and I worked for AT&T Bell Labs all my career. And then I retired and moved out here 20 years ago. But I enjoy this stuff. And it really kind of bothers me that we don't have more science exposure to people. And the fact that people still believe, a large fraction of people still believe the Earth is 6,000 years old. And it'd be a joke, except you see that our head of education doesn't believe in evolution. The guy that's head of EPA doesn't believe in global warming. All that kind of stuff. And about 45% of the people are pretty sure that the Earth is only 6,000 years old. 30% of them know in their heart that and I know because I've gone to these people's talks. I don't go to their religious stuff, but I go to a lot of their talks and discussions and so on. I've taught courses on it and stuff. I've had them in my class, and it just boggles my mind. I don't understand how they do it. But yeah, it absolutely is. Yeah, it's crazy.
Doing great.
Good.
Not only in the United States, in Europe, do they feel the same way? Percentage of people who think that
Oh no, we're the crazy ones. I mean, a lot of the religious people came from Europe over here. They were kicked out, right? And I'm sure there are some, but I don't think Europe has anywhere nearly the percentage. Actually, a lot of the Europeans aren't nearly as religious as Americans are, I think. I haven't really looked into that, but
you're probably right.
I think so. Yeah. I guess we're getting close.
I mean, I'm real serious. Yes, I can see that.
Okay, why don't we try to get together again?
Snakes and alligators.
Okay, why don't we, I think you still have one coming, but... Okay, so we're going to be talking about radio astronomy for a little bit now. Of course, radio waves are electromagnetic waves very much like light. They just have a longer wavelength. So they are caused by different reasons, and they have different impact, and they give us the information that's different. One of the things I'd like to point out is that the hydrogen atom has a nucleus that's a proton, and protons have a spin, okay, and a small magnetic field. And the electron is effectively going around the central part, and it also has a spin and has a charge. Now, it turns out it has different, because they have a spin and they have a charge, whenever the spins are parallel, they have one energy, and when they're anti-parallel, they have another energy. The amount of energy difference is just the equivalent of the amount of energy in a 21 centimeter radio wave. So when it flips from this to that, it emits the energy to get rid of it, okay? Or it has to absorb energy it has to absorb energy in order to be parallel to it. So it either emits or transmits at 21 centimeters. Now, in addition, you have a Doppler shift if it's moving toward you or away from you. That gets shifted by a small percentage, okay? But what that means is that if we look at 21 centimeters emission, we're looking at hydrogen, and hydrogen is everywhere. It's like still 90% of the stuff that's out there in the universe. That's what goes together to make stars hot and burn and so on. So if we take a radio telescope and we can get incoming radio waves of all sorts, but 21 centimeters particularly interesting to us, and we can survey the sky, and we can make now the wavelength of light is very tiny. Radio waves are much bigger, so you don't get the same resolution that you get with a wavelength of light, but that's okay. We get a lot of other information also that's very interesting. Here was the first radio telescope in 1931, kind of crude. Here's one of the most recent ones in Arecibo, Puerto Rico, and this is huge. This is across a valley, and just a quick story there. Several years ago, my wife was working with a woman in Europe, and the woman in Europe was going with a guy from Australia. Long story, right? And the guy in Australia was, his family was into radios and stuff, manufacturing high-tech radios. So he got interested in search for extraterrestrials, okay? Which, of course, this would be a prime thing because it really pick up an awful lot of stuff, and you want to do that if you're looking for people really far away. Well, it turns out that we met with them once in California, and at where they had their SETI headquarters. Actually, it was kind of fun. And he was telling me that they got an offer to go to China because China wanted to get into this business, and they had a place in China that had a similar bunch of hillocks. See how these are hillocks around here? That's kind of ideal to make a big radio telescope because it's already half dug out for you, and then you just clean it up a little bit and you go with it. And he said, man, they brought us in. We got the first-class treatment. We had a big dinner to celebrate our arrival and all that kind of stuff. And he said, he's telling these guys, he said, look, I don't have that kind of funding back in Penn. I'm just a hoi polloi guy, okay, back in the United States. I don't have that kind of money. Oh, don't worry. Because they were trying to lobby him to get the next big telescope like this funding to go into China instead of someplace else around the world. Turns out that they were successful. Here is Arecibo still. See these people down here walking on the surface? Okay, that's how, and they walk on these things like water skis so they don't poke through. Okay, it's really kind of neat. I mean, it would be fantastic. And here's the Chinese radio telescope. See the same kind of hillocks around here, and this is what it looks like. It's just been finished within the last year or two.
Because of China's pollution.
I'm sorry?
Where would that be? Does pollution have anything to do with it?
Oh, no, pollution doesn't have much effect on this, but I don't know exactly where it is. I think it's in the, you can find it online. I should put a map up here, but I don't remember offhand. I thought I had a comparison size also. This is about, the Arecibo thing would fill in about here. So, I mean, it is huge, comparatively speaking. And the Arecibo one is the one that they use to listen to Voyager, which is going out beyond our solar system and all that kind of stuff. It takes, I don't know, a day and a half for the signal to get to there from here. And, of course, it's really faint, but that's why they use Arecibo, this huge radio antenna, to listen to. Yeah. I'm sorry?
What do they do with the rain when it rains?
You saw the other one where he's walking on a wire mesh. It's a wire mesh. Yeah, it just goes right through. So as long as you have a wire mesh that's smaller than your radio, the radio wavelength is 21 centimeters, and your wire mesh is maybe like this. But that's why they walk on those water skis. Okay, here's a galaxy. If I look out in 21 centimeter radiation, very large array, and this is in, I think, is it Arizona? Might be New Mexico. I've flown across it in an airplane going back and forth, and I could look down and see this array. It's pretty large. It looked kind of tiny down there, but it's obvious once you're looking for it. So 28 antenna dishes, each of them 81 feet across. So you can see this is pretty huge in the scale of things. Here's another one of the really big ones. This is about the size of a football field that they're moving around. You can see the people in here, pretty small, give you a little bit of the scale. So there are several of these around the world because it gives a lot of very interesting information. Now here's one of the radio sources. Here's some source where there's been a big explosion, probably where things fell together and accumulated, and then there's a lot of other stuff that's falling into that, and it falls down in along the poles where the magnetic field then ejects. As it falls in, it emits radiation out and hits these gases out here on both sides, so that emits an awful lot of radio waves in all directions, and that's what this is a picture of. Okay, so now we can study that a little bit, and the very large aperture gives this one, National Radio Astronomy Observatory. And one of the things that's neat about radio waves is that they're long enough and slow enough that we can actually time them, okay? So, it takes about 1 nanosecond, 10 to the minus a thousandth of a millionth of a second to go from here to here, about a foot. Okay, well, these days with electronics, I can divide that up into a gazillion pieces, okay? So instead, with light waves, I can't do that. But with radio waves, I can do that. So it's possible that I can say, hey, this guy's going to look in a certain direction, and I'm going to record all that very accurately on tape or some recording magnet. And over here, I'm going to get these other guys to look at the same thing at the same time and record all that stuff. And then we'll get them together in the laboratory and we'll combine them. Now, it's effectively like having a telescope that's as big as from here to here. Okay? So, because I can electronically combine these things, it's the same stuff. Okay? And what that means is that I end up with a very, very, this is 1/10 of a light year across, 4,000 light years. Angular resolution is now, this is in 2001, so good that if your eyes had that resolution, then from Portland you'd be able to read a book in New York City. In a few years, I mean, that is absolutely incredible. But that's because you are able to time these things that are so far apart in the Earth. Here's just another one. Also, for instance, you can find out, because of the Doppler effect, one side of, if I send out a radio beam, and they've done this to the moon, and now they've done it far enough, they have enough power and enough sensitivity that they can do it with other things. Here they did it with Mercury, and one side is moving toward us as it's rotating, and the other side is moving away. Well, that gives a little bit of a Doppler shift. That motion changes the wavelength just a little bit, the frequency, the wavelength, so that I'm able to get that. So I'm able to find out what the rotation of Mercury is using these radio telescopes. So it gives it quite different information than optical light does, but it's also got a lot of pretty interesting information. 1965, this is the antenna first detected radiation from the Big Bang. This was Bell Labs, which is where I worked for a while, not at this location, but I mean, Bell Labs is 27,000 people, so, I did not associate with these guys. I was just part of the hoi polloi. But anyhow, this was, and they didn't realize what they were doing. They were studying transmission of radio signals from one side of the United States to the other side of the United States, but they had this background noise. They didn't know what the hell it was. You got to get rid of all the noise if you want to transmit telephone conversations, right? And they didn't understand until somebody said, hey, go talk to these guys down at Princeton. They've been thinking about putting together an experiment like this, and I think you've just done it. They found the background radiation of the universe, and they didn't realize it, but that's what they found. They were the first people to discover it, got a Nobel Prize out of it. Here's just another big telescope. Here's another one. have limited motion of where it can study the sky, but of course the Earth is rotating, so it's sweeping a large part of the sky all the time anyhow. Here's a few more. Some of these are ones that were put up into the sky. Some of them were ground-based, but they gave a lot of information about the background radiation of the universe and gave us a lot of good information about how old the universe is and so on. Also, there are X-ray telescopes. You look at all kinds of radiation you can, because every bit of radiation gives you a different kind of information. So here's an X-ray telescope. Now, you can't focus X-rays, but what you can do is you can bounce them off the array. So here you have something that has an array of atoms that are separated by a certain amount. So you diffract it because there's an interaction that happens with waves that allows them to actively interfere properly. So you can focus these things this way. So you end up having a whole bunch of things angled around like this. And then the X-rays come in here and they bounce off these materials and they bounce off again, and you can end up focusing down here. So you can now focus X-rays and get some information about X-ray part of the spectrum, which is additional information also. Here's actually the telescope, and of course X-rays don't come through the atmosphere, so you got to put it up there, okay? So this is circulating the Earth, and the Chandra X, let's see if it says, sensitive wavelength between 0.1 and 10 nanometers, 4,000, I forget, I don't want to give you wrong information. Instrument produces X-ray images comparable to those attainable with optical telescopes. This is the normal image, and this is the X-ray image. The X-ray image lets you go through a lot of this stuff and see what really caused this, and this is something that blew up, and a supernova, and it collapsed, and now we can see in here through these other things because the X-rays, different wavelengths, and it's not interfered by all these other gases and so on, and we can go and look at that with X-rays and understand more completely what actually happened back in the day. Here's the center of our galaxy, the black hole at the center, and of course you look toward the galaxy, and one of the problems there is there's so much gas, hydrogen gas, dust, just stuff floating around that infrared and other optical kinds of things just don't get there. But X-rays can, in fact, transmit a little bit better. We're getting better and better at this all the time with radio waves and trying to bring all different kinds of things to focus on this center. Let me give you a little bit about the scale. Maybe I should have done this earlier, but if our solar system is a quarter, our galaxy is North America. Okay, so the galaxy is really pretty big. If our sun is a quarter, the nearest star is 400 miles away. Okay? Solar system orbits the center of our galaxy at about 537,000 miles per hour. So you think you're going around on the Earth, at the equator, you're moving about 1,000 miles an hour as you go around once a day. Well, you're moving 537,000 miles an hour around the center of our galaxy. I don't feel that. If the size of the galaxy is a quarter, the nearest galaxy is 1.5 feet away. So there's a lot of galaxies, and they interact very strongly with each other. We can see lots of pictures where gravitationally they're drawn toward each other and they go through each other and smash each other up, okay? Tear things apart. Lots of interesting stuff. You can learn from that because of the way the gases interact, the stars interact, and so on. And ours is going to do that at some point with another galaxy, but we don't have to worry about it. I just showed you this picture. This is the one that I used to take pictures with. Oh, this is Galileo. Telescopes of the world. Oh, I guess, gee, is that everything? I think I finished up. Gee, surprised me too, yes.
Some of these are privately owned, some of them are corporate. Can you talk about the politics of the telescopes?
I think for the most part, a lot of these are by foundations. I don't think they're privately owned. Well, they're privately owned in the sense that some university or some foundation might own it. And then you give money to that. And one of the big things is, and the reason some of these have people's names on them, is because, yeah, I'll give you $100 million if you name it after me. And that's a real tough sell to get to all these things. But on the other hand, we have so many people around now with billions of dollars. I don't expect to see a Trump telescope, but But the thing is, there are a lot of people, and it's just that some of these other wealthy people have decided to put their money into other things. Because, what do you do with $50 billion? And there are a few people around like that. Well, they're going to support this or that. The guy that had Microsoft, he and his wife are into education. They're into helping people in Africa, getting rid of malaria. And those are all good things, too. It's a matter of where your focus is. Yeah.
Now, we were talking about telescopes. Now, if we switch the subject to microscopes, are we just doing the opposite, or is it the same physics?
Well, yeah, the optics is pretty much the same, except for the most part, you're not using mirrors. You use mirrors because that gets you bigger. But also, you're limited with respect to the wavelength of light there, because you're going down smaller and you're getting closer and closer to the wavelength of light, and that means that your resolution is not good beyond a certain point, which is why they go into electron microscopes. So with an electron microscope, you can get much finer resolution because the wavelength of an electron, yes, we all have a wavelength, the wavelength of electron is much, much smaller than that of wavelength of light. So you can get much better resolution.
We're trying to make them small, large, right?
Right, so you can see it. Right, and actually they've got well, I can go off on another whole tangent, but yeah. So, but that's kind of neat. Yes.
So who coordinates when you were talking about merging their findings with these findings to do some comparisons? Who coordinates with that?
Well, the way you get funding for a lot of these things is to go to the government. Our United States government puts aside a certain amount of hundreds of millions of dollars, maybe $1 billion or $2 billion, for science, and then scientists in charge of that decide. You make a submission of what you want to do, and then scientists that are knowledgeable read through all that, and if they don't know enough about this, they'll send off, just like with reviewing papers, they'll send this off to somebody that's an expert in that, an expert in this, that's not involved in the project. And so they evaluate things, and then it comes down to who's going to get the money and who's not going to get the money. It's sort of like whenever you're trying to get something up in space, you have to submit it to NASA. And then they have a bunch of scientists say, well, we'll learn this about that, but we have this other project that's going to include that too. Why don't you work with them and then we'll get together? Or no, we're not going to do that. We think this is more. It's all those kind of trade-offs. So I think it's not so much political, except for getting the initial funding, for instance. And where I mentioned where these guys that were flying the airplane with a telescope in it were complaining about NASA was getting all the money from the government and much less money for real space science kind of work. They were complaining about that, but that's a decision that was made politically in that point because NASA gets it. But once NASA gets it, then they decide whether we're going to go to Mars or whether we're going to put another Voyager out there or whether we're going to send something to go around and study Jupiter or whatever, okay? There's a lot of exciting stuff going in that direction too, because there's possibility of life on Europa, some moons around other things. So they're putting together things to go out and do that. And there's just all kinds of things vying for this scientific money, and, well, on and on. Yeah.
Is that funding in jeopardy under the current regime?
Well, I think it always is in terms of quantity. They're not going to cut it off completely, okay? But instead of getting, $3 billion, you might only get $2.5 billion. Well, all these things are very competitive anyhow at $3 billion. And if you're cutting out 15-20%, well, that's a big hit. So, yeah, it's always a problem. And unfortunately, it's going to get worse before it gets better, I'm afraid, with the situation the way it is. I'm really pleased that we have some really top-notch, brilliant people going into science still, because it's just so damn much fun, and it's so exciting that you really need to give them the money to do it, and so on. Yes?
Does national security put much of a pall on this?
Not so much on this kind of thing. I did mention earlier where the government, whenever they were doing satellites initially for some of the technology and so on, I suspect there might be some areas. It certainly is true that traveling from one country to another is not always so easy, especially with Russia and so on. And I can see the reason for that if there's competition, depending on what the subject happens to be. Certainly China is trying to get on board big time with a lot of these things. They want to be numero uno in space, in science, in just about everything. One comment to give an indication of what's involved, I remember the stealth program before we knew about stealth bombers and stealth fighters and all that kind of stuff. That really was based on a Russian paper. There was a guy in the, what was it called? Not the smokehouse. There was some secret place at one of the air fields. I'll think of it in a minute, maybe. And this guy saw this paper and he took it into his boss and he said, "Hey, you know, what this says, you do the calculation, work some of this stuff out. This says that we could make a stealth thing, okay? We can make all these things cancel out. We could shed them off in other directions instead of radars kicking it back." And so they developed that, and we ended up with stealth technology before the Russians did, because they didn't fund it. But on the other hand, it's their paper. So if they would not have let that around, we would not have stealth as quickly as we did. And I think that's why, for instance, the CIA and other people that are having satellites that are looking down on Russia and so on didn't want to tell how you compensate for the Earth's atmospheric variations. It's all those kinds of, so there is competition in that respect. With respect to some of the big stuff, like CERN, where they're putting the big collider that discovered some particle things, they're doing a similar kind of thing with the Stellarator, where you're trying to smash nuclei together to get to, like the sun does. You put a couple of hydrogen atoms together to make a helium atom, and you get a lot of energy out. They're working on that. Now they have a big project. I think they've donated $50 billion to something like that going in Europe, near where CERN is. So there is a lot of cooperation worldwide to certain things, but I'm sure there are always niches off to the side that they keep quiet. Yeah.
Can things be weaponized? Like ray guns?
Yeah, they tried doing some of that stuff, but it's really hard. I mean, some of these optical laser kinds of things. But compared to the energy in a really strong laser beam, compared to a shell blasted out there at the same speed, or even much smaller, it's nothing compared to the impact of a bullet or an explosive bullet. So, I'm sorry?
We use a lot of these things for crowd control, anti-riot type of thing.
Oh, well, there is the sound thing also that does it. There's rubber bullets, there's water cannons, all kinds of stuff. But in terms of, one of the difficulties that they're concerned about is, one of the things that happens whenever you have an atomic explosion is a very strong electromagnetic pulse. And I know even whenever I was in Bell Labs, I designed integrated circuits and stuff, and one of the things that some of the people were working on was designing integrated circuits that would not be taken out by this electromagnetic pulse. So you had to have a special things on the input to short that out so that some big explosion wouldn't get rid of all your equipment. And that was a big deal. I'm sure that was very carefully guarded so that information didn't get around very much. Yeah.
With all the reviews and so forth in place, how did Hubble how did it pass through and get launched without somebody discovering it?
Oh, well, I think that was because somebody screwed up. It's like I give you $100 million to do something or other, and yeah, that works great, but oops, this guy tripped in the shop and he slammed it down and he cracked this, but I'm not going to say anything about that, except, I mean, it wasn't like that, but they did the best they could, and it's not like somebody screwed up in terms of because of funding or anything like that. It's just that they did the best they could, and they still goofed. It's very similar to the guy, remember several years back, where there were a couple of people working on putting a planet, I think it was around a satellite around Mars, and this guy gave the numbers to France, and he did it in feet and inches, and they interpreted it as meters and centimeters. Boom, gone. I mean, it wasn't intentional, but things happen.
Didn't they test it before they launched it, before they put it in this,
Well, they did. They remember that it's just that the interference compared the wrong thing, and they didn't realize it because that non-reflecting surface had chipped off, so they were reflecting from a different surface than what they thought. So they thought everything is A-okay. Yeah.
Has that been corrected, that?
That's what they sent the space guys up, and they changed it out. They put a correction mirror in. It's like they put a correction lens in front of your eyeglasses in front of your eye. Yeah. Yes.
To weaponization of some of this technology, do you have any ideas about what was going on in Cuba with the sound?
With the sound?
The
People
diplomats.
People have illnesses and.
Oh, yeah, I have no idea. Could be that they have something really going there and it just irritate the hell out of people and make it hard for them to work, like that's indicated. But I mean, there's always stuff like that going on. One of the big things, this just comes off the top, one of the big things that we did with the Russians in England, they did. Back in the old days when you put in keyboards and stuff, and to enter stuff into your big computers and stuff. Well, it turned out one of the people in MI5 or 6 or whoever in England realized that every time you put a key down on your keyboard, it made some electromagnetic static. So they got a room next door in a building, and they would record all these statics from the keyboards, and it was such that it was unique enough that they knew when it was an E or an A or an F or whatever, Russian, and they could pick that up. So they read all their stuff before it got encoded, before it got sent. Okay? So it's those kinds of things that you play games with. You're not going to go around and say, oh, by the way, you're making an awful lot of noise with a keyboard. Make those keyboards different. They're just saying, keep it up, keep it up. Yeah.
The thing that my understanding was in Cuba, there were these American diplomats at the embassy, and that there was some kind of sound interference that actually damaged actual physical illnesses.
Yeah. 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 And there are things that are, sort of subliminal, that is, you don't hear it really with your ear, but it bothers you. And I know that, I forget where it was, but I remember hearing about they would do that to keep people moving along. So you didn't stand in front and take up the time because they wanted to move people. So after a while, you'd feel, you'd move along. Yeah.
what did the O stand for in that owl telescope?
What's that?
Overly large,
I mean,
over large?
I don't know. Maybe. Yeah.
I'm just think that they come up with better names than large array and very large array. Incredibly large.
Scientists are only creative with the science, not with the English, okay? Have you ever read a science paper? Not very creative. Yeah, George.
You showed Galileo's telescope, and that did get him into trouble because he went against, he was inconsistent with church doctrine that said the Earth was the center of the planetary system, and he said, no, it's the sun. Well, that made him a heretic. So they brought him down from Florence to Rome and put him to the Vatican, put him on trial, and they sort of cut him a little slack, but he came, what they did with heretics, they burned him at the stake. So he came very, very close to being executed.
Yeah. Well, one of the problems was also that because this was going on for a while, he was one of the big professors at one of the universities there when he was doing all this kind of stuff, and he was very buddy-buddy with a lot of the popes as they came along. So he had kind of an in with some of the higher members of the church and so on. He had some people on his side. But one of the things he did was he wrote a book, and the book was about, it's sort of like a student learning from the professor kind of thing. This guy would make some stupid statements, and then the scientist would explain to him exactly how things were, and he'd make another stupid statement. Well, it turned out that because of the way the names were said and the way it was couched and so on, it was pretty obvious the stupid person was the Pope, and the smart guy was, not the Pope. And so that was another reason. But whenever they had this trial, the recommendation was that he be. But one of his buddies, one of the archbishops, said, no, we don't go that way. But even then, he backed off, which was unfortunate. But in those days, they didn't fool around. This guy that was burned at the stake in 1602 or something like that, who was talking about other gods and so on. Well, he wasn't, I thought it for a long time, he was just another dingbat that were burning at the stake. That guy was one of the smart guys at the time, and he had vied for the same position at Padua University that was finally gotten by Galileo. Yeah. So he was not a dingbat, he was a really smart guy.
Well, Copernicus, 100 years earlier, had come out with a theory that
Right. Yeah. Well, there were lots of people that had those kind of ideas. It's just that, yeah, and it's the same thing. I remember reading about, I told you about they knew about lenses and so on a couple hundred years before. Well, there is a reference to some farmer who had put a couple lenses together and said you could see things pretty well at a distance. But he was just a farmer, and he didn't publish it. It just was in some minor writing to, I don't know, a friend or whatever. But when they go back and delve into all that kind of stuff, it came across. But it didn't get highlighted. He didn't get credit for much of it, except in these existent things like I'm telling you now. But it wasn't really pushed to the front where people picked it up and used it. And, of course, Italy at the time was the center of knowledge at the time. The Germans would go down and you had to learn learn Latin, because Latin was the language at the time. So they had to go down, they learned Latin, and they went to school there. Einstein did that. He had to go down, and he ended up, I guess, I don't know if he learned Latin too well, but anyhow, he went down to, when in his early years, he went down and got educated there, and then came back to Germany and did some things, so, yeah. Now you go to, I'm not sure where. The United States still has pretty good graduate schools, but again, see, I'm not sure how long that's going to last because the funding just isn't there. I cry when I read about all this hassle about funding for school systems. I mean, undergraduates and stuff is where you really get started and where you help people. And our attitude is just not in that direction. A few years ago, the top national people in one of the big national contests, they were 10 Indians in West Portland. And I'm sure they were from the families of the Indians that were working at Intel or something, where they have a culture that says education is the name of the game. I was fortunate. I grew up in a family that wasn't particularly educated, but they had an appreciation of education, and all of us were three sons. We were all encouraged to get an education. And that makes a big difference. But I can go on with our Secretary of Education, but I won't go there.
We got enough money to build a wall, don't we?
Yeah. So, okay, well, thank you all for coming. I'll be hanging around if you want to do anything.